Okay, so welcome everyone to the Modern Machining Methods webinar series. My name is Dan Perry. I'm the Eastern Applications Manager for DP Technology. And today is going to be part one of a three-part series that we're doing. And today's section is Essential Milling Practices. So for today's presentation, we're actually going to break it up into three parts. The first presenter is going to be Brent Marsh. Brent is the Automotive Industry Business Development Manager for the Americas and has been with Sandvik Coromant for 16 years. And Brent's going to be talking about the M5 series cutters. Following Brent, we're going to have Kevin Wismer. Kevin is an ESPRIT applications engineer, and he's been with DP Technology for 4 years now. And Kevin's going to be talking about profit milling and high feed cutter programming. Lastly, we'll have John Pusatera. He is a senior training specialist with Sandvik Coromant and has been with Sandvik for 19 years. John's going to be talking about Sandvik's Speeds and Feeds app. So throughout the presentations, we would encourage you to go ahead and ask questions via the chat utility in the GoToWebinar software. And Freddie Wilson, who is a Sandvik machine tool solution specialist and has been with Sandvik Coromant for 20 years, is going to be answering questions via chat along with myself. Freddie will be fielding all of the Sandvik related questions, and I'll be answering the ESPRIT questions. And then at the end of the session, we'll have a live Q&A where we'll probably answer some of the more frequently asked questions that transpired during the session. And we'll do our best to get to everybody's questions. But if we don't answer your question during the session, we will follow up with you individually after the session is over. So without further ado, I will go ahead and turn it over to Brent.
Okay. And I'm getting my screen going here. Okay, here we go. Okay, Dan, thank you for the introduction. We appreciate that. Again, as you mentioned, I'm my primary focus with Sandvik Coromant is automotive business. So that being said, we know that today a large percentage of the machining and automotive components is aluminum, and that amount is growing every year. So we know that aluminum is a relatively easy material to cut, but it does have some challenges. And typically those challenges are surface finish requirements, flatness requirements, and clinging burrs, because the material is very ductile. So it's often a problem to get rid of burrs. That being said, typically you can mill an aluminum surface quicker, faster than you can deburr it. So you may have just a few seconds milling a surface because it's such a high rate of speed and feed, but then you got to go back, you've got to either hand deburr it, or you've got to have a brushing tool in the spindle, something else to go over and remove these burrs. So our customers, both end users and machine tool builders, have come to us over the years, and recently they've said, hey, Sandvik, help us, we need to get rid of burrs. If you can come up with a design, a face milling tool that can get rid of burrs, it would be a huge benefit. So we have an engineering team in France that took on this challenge, and the tool that they developed, the first one I'll talk about, is what you see on the screen, is this M5 series of cutters, and the M5B90 over here in the left-hand side where my highlighter is here, my pointer. That's the very first tool they developed. And as you can see, it says 1 millimeter AP. AP is the axial depth of cut. So it's a finishing tool only. And then from that tool evolved a number of different designs. So we came out with a M5C90, which is the next tool here, has roughing capability added to it. We came up with a brazed type tool that's a similar technology. And then over here on the far right, we came up with a roughing tool. That's for cubing operations. So we've included that. So move on and talk a little more about the M5B90, the very first tool we developed. So the key here is it's a broaching technology. Each insert takes a little bit more depth of cut than the next, both axially and radially. But each insert is like a little high feed insert within itself. It's a one effective cutter because the highest tooth controls everything. That's this tooth with the red dot. I'm going to go ahead and let this turn here, and then I'll stop it again. Okay, so yeah, you have number 1 through 10. This particular cutter has 10 inserts, which most of them do in this design. So, you know, here we talked about taking 1 millimeter depth of cut. You're dividing that by 10. So roughly 0.1 millimeter per insert in axial depth of cut. But this is your highest tooth. And that highest tooth right there is what you would preset and get your diameter and your height before you put the tool in the magazine and told the program, you know, what the size of the tool is. So that's what you would set it off of. But there's no adjustment on any of these inserts. It's a very easy tool to set up, unlike a lot of the competitive tools that are out there that have very complex presetting requirements, especially when you talk fine finishing and when you want to get rid of a burr and that kind of thing. So I'll go ahead and let this thing rotate on around. It's going to show you this, the rotary broaching concept. See, each insert, more depth of cut. Put them all out on a straight line. So just like a linear broach would be. So anyway, so typical parts that you would see are these housings, valve bodies, cylinder heads, blocks, everything with passages, with cavities, lots of places for burrs to hang on, and always tight finish requirements because of gaskets, sealing surfaces, you know, waviness requirements, et cetera, always tough. And that's always been the challenge. So the benefit of this tool, good surface finish, good flatness, extremely good tool life, elimination of the burrs, no run out problems because you don't have to worry about one insert to the next because each one is set to a different height. No presetting required. They're all fixed pocket. And we can even put the same insert in every pocket if we want. And I'll talk about that a little bit later. The thing to remember is that these are not shoulder mills. These are face mills, much like you would think of a 45-degree face mill. You don't mill into, they're not designed to mill into a corner. And the outer diameter of the tool is larger than the effective cutting diameter because of this step technology. So here's another look at it. Again, 1 millimeter depth of cut. The feed per revolution, roughly around 3 millimeters per rev. So that makes it like a high feed insert, basically. So your axial, the axial thickness is 0.1 millimeters. So the chip is 0.1 millimeters thick, but the feed rate being 3, it's 3 millimeters wide. So that's a little fine ribbon that you're cutting, just shaving material. Here's another view. You can see the step technology. This is what you get in the corner. Each one of these being like 0.1 millimeters higher than the next. This is, of course, it's exaggerated. So traditional face milling, you put every insert on the same plane, both axial and radially, and when it exits the part, you get this burr pushed over. That's the problem. With our concept, you're shaving the material. No burrs, just a little fine, I mean, the only, it might be a microscopic burr, you know, very, very little, acceptable in most cases to the customer. The inserts for these tools, I mentioned that you can put the same insert in every pocket. Well, that would be this one here that's circled with the red. You know, it's a 200 millimeter wiping radius, so that surface right there has a bow to it of, you know, very, very, very slight, you know, at a 200 millimeter radius. So you can put that insert in every pocket in most cases. That being said, we do have standard inserts for the other pockets, 1 through 9, and then you would put the wiper insert up here in pocket number 10, okay? But why have the confusion? The price of the inserts is the same, so it's not like it's a savings here to go with these. So in most cases, it works just fine to put in that wiper in every pocket. The other thing we can do to make it more economical, if you're not doing real high volume work, like making hundreds of thousands of components, you're just making a smaller number of components, but you want this technology, you can put a carbide insert in the roughing pockets. So 1 through 9, we can go in with this carbide insert, and then just put the diamond insert, the PCD insert, in the final insert pocket number 10 to achieve the right finish. That's another thing we do. So, the mounting configurations, about anything you can imagine. These tools are all custom solution. They're pre-engineered as far as the pocket design and the placement of the inserts, but in terms of diameter and mounting configuration, etc., we can make it to whatever you wish. Solid tool, this one here, this is a solid steel tool. This is a traditional Facemill mount tool. We've got ring cutters, like this one over here is a ring cutter, the adapter plate for that. The other thing we're doing, if you go to this left-hand corner over here, this is a 2-piece construction. It's an aluminum body that's anodized with a hard coat, and then a steel ring that holds the inserts with the pockets, so you don't have wear or deformation. Okay, so that steel ring it's actually heated and put on with a shrink fit method, so it's very, very tight, and it's key driven. So anyhow, this is quickly becoming our go-to solution right here, because it reduces mass, it's easier to balance when you're running super high RPM, better for the tool changing operation to reduce weight, that kind of thing. So when you think about these tools and you think about, okay, how do we program them? What do we do that's different? Well, really, there's not much you do different. Good face milling practices. We always suggest climb milling. So as you can see here, we've got clockwise rotation, climbing onto the part, and that way you enter into the cut with a thick chip and you exit over here with a thin, basically 0 chip thickness at exit. That's the preferred way to face mill. The cutter position should always be slightly to the offset, like you see here. So we've got 70% of the cutter diameter is the width of the cutter path. You want to do that whenever you can. And that should be your guide as to cutter size selection. If you know how wide your cutting path needs to be, you should select a cutter that's about 70%, or I should say 30% greater in diameter than the actual cut width. Also, you got to consider the rigidity of the part, what kind of fixturing method you have, horsepower, torque, at your spindle, what kind of spindle adapter. Is it a 50 taper? Is it a HSK 80? Is it an HSK 63? Whatever, those things factor into how big of a tool you can run. So keep all of that in mind. The other practice we talk about all the time at Sandvik Coromant is rolling on. This rolling on method, again, we're rotating in a clockwise direction, and then as the tool enters into the cut, it rolls basically like there's a pivot point right over here. See where my highlighter is? It rolls onto the cut, and that reduces vibration when you enter the cut, which of course helps tool life. It makes less noise. It's quieter on the entry. And then of course the surface finish is much better. Sometimes if you just go straight onto a part, you can have some of that vibration. It can impact the surface finish, and you'll have a little bit of a witness mark on it, especially if you're trying to do a fine finishing cut. So anyway, just something to keep in mind. After we're done with the presentation, we've got some videos that we're going to show, and I'll show you an example of how we do that. So here's a customer case. This is a very good example. This is a transmission valve body, and you can see you've got all these worm tracks over here. These things are, whoops, sorry, I got ahead of myself. got all these worm tracks over here on the surface. In this case, the customer was, he was having to come back and brush the part. He had a brushing operation in the machine. So he would mill, and then he would tool change, and he would come back, and the brush was actually, like I said earlier, the brush was actually slower than the Facemill. The tool that he was using had 18 inserts in it, okay? The depth of cut, axial depth of cut, only 0.3, so 0.3 is like 12 thousandths. That's not much. So with that being said, we could do it with only 5 inserts. We didn't need 10 inserts in the cutter. We only needed 5. So we built a cutter with 5 inserts versus the 18 that they had. We were able to run it at a little higher RPM. So we were up to almost 4,000 RPM here. And we were able to increase our feed in millimeters per minute up to over 7,000, where it was just over 5,000. So significant increase in feed rate. And everything else kept the same, basically the same width of cut, 135 millimeter width of cut, was 160 on the cutter diameter, same depth of cut axially. The tool life, look, they were getting 8,000 parts, and at 8,000 parts, the brushing operation could no longer clean up the surface. So the burrs were so heavy that they'd have to pull the cutter, put a fresh cutter in, so that the deburring brush would do its job. Of course, we eliminated that deburring brush, so they don't even need it. So that being said, we could go up to 30,000 parts before there was enough of a burr that they thought, okay, we need to pull the cutter, we need to go in with a fresh one. So that's a significant increase. So tremendous cost savings, cycle time, cost per unit, etc. So from the M5B90 that we just talked about, evolved this new cutter with roughing inserts around the perimeter. We call it the M5C90. It's essentially the same tool, but it's got some higher depth of cut inserts. So with this, in this case, we can combine 2 tools into one. So in a lot of cases, we can do rough and finish in one pass with this tool. Not always, really kind of depends on what the final requirements are. Rigidity of the part, how good the fixturing is, how much how much you can rip off at once without vibrating too much. So we might still have to rough and finish with it, 2 passes, but you don't have to tool change because you got one cutter. So traditionally you have a roughing cutter and you have a finishing cutter, and that's what we've rolled into one. So what you can see here is the you've got this green band around here. See that this green band around here is the roughing band. The blue band is the finishing part. And if you look over in the right corner, this is the roughing insert right here. You can see where it allows more depth of cut. What it gives you is around 4 millimeters, although we've pushed that up to 6 millimeters recently without any problem. So originally we said 4, but we can go more. So an example here where we applied this thing, this was a housing for a brake system for a truck, and you can see the surface over here. You've got all kinds of like ejector pin, gating, rough stuff that has to be milled up. Those things were proud like 2 millimeters high or something. Here it is fixtured. Here it is after it's machined. We were able to put carbide inserts around the perimeter of this tool and PCD inserts in here for the finishing portion of it. So awesome solution. What evolved out of the M5C90 is one we call the F90, and this one has brazed inserts in it. And this thing's got these PCD brazed blades that are finished with a laser. And that's how we get the accuracy and the consistency and the perfect edge prep. You can't have a dead sharp diamond insert. A lot of people think they are, but no, you have to have a very, very, very slight hone on it just to keep the edge from fracturing. And that's what we do with a laser. The final cutting is done with a laser. That being said, we don't retip these tools. They're treated basically like a disposable tool, I guess you could say. Of course, you can recycle the metal that's in it, but we don't recommend sending them back for retipping because it's just too hard to replicate what we do from the factory. So we've got a very good process for making these tools at a very efficient way. So it's really no savings to retip it. But they're designed for thin wall parts and smaller diameters, maybe smaller machines with real high RPM, you know, smaller, like even a brother machine that has real high speed, you know, something of that nature. We go all the way down to 20 millimeters on the cutting diameter. The biggest one is at 73. And these are a on-the-shelf solution. They're available, not custom engineered. So here's another look at it. Thin wall parts. You can mill up to the shoulder with these cutters, but you're going to get, it depends what kind of finish you need. You're going to have a little bit of a choppy finish. So you have to look at what your part requirement is. The final member of the family is the M5Q90, and the M5Q90 is a cubing cutter, and that cubing meaning removing a lot of material right from the foundry, the raw cast stuff. A lot of the foundries will do the cubing operation and then send it on to a production machining facility somewhere else. So this is the right tool for that. And these are totally a custom solution. They've got, you know, a number of different inserts depending on what you're doing. You know, in this case over here, this tool is doing a lot of sidewall milling too. So like down inside of a cavity, maybe a bearing cap area in a cylinder block, for example. The tools are designed to have an anti-ejection feature. So there's like a little dovetail feature in here that secures the insert in the pocket so it doesn't put all the load on the screw, because you throw an insert out at high speed, it's very, very dangerous. So that's why we developed this locking mechanism. I don't know how well this will come through. It's in slow motion, but I'm going to stop it here, and you can see what the inserts look like. They are adjustable, or you can put an adjustable feature in if need be. We have that possibility. But that's just a closer look at it. So that being said, that's all I've got to present on this family M5 series of cutters. And I am going to hand it back over to Kevin. And then Kevin is going to run some of these videos. So I'm going to change back to, okay. All right. Okay. Okay, here, Kevin has got
this is the climb milling video.
Yeah, okay. So we have an example here. We're going to talk about climb milling. And on this video, you're going to see the cutter enter the cut, go all the way around the part in a clockwise fashion, offset, like I said earlier, you know, where you're not right dead center, you're offset, going around the part. Then it's going to drop down in this center feature, and it's going to reverse direction, which is still climb milling, but it's going from inside out. So that being said, Kevin, if you want to go ahead and run it.
Okay. Very good. Brent, I'm going to go to the ramping off video. Or actually, I do the rolling on video now. And you may be muted, Brent. that was an illustration of the rolling on that Brent had been talking about. And this is going to be an illustration of ramping off that he had talked about as well. So here's a quick clip of that. All right, so those are just a couple of videos kind of illustrating the concepts that Brent was talking about. And I think I'll go ahead and go into my presentation now. Just give me 1 second. Okay, so my name is Kevin Wismer. I've been an applications engineer with DP Technology for 4 years now, and I'm gonna go ahead and talk to you about what profit milling is and why it is a fantastic solution for all of your high volume material removal needs. So profit milling is a strategy, a machining strategy that combines concentric out with what's called trochoidal milling, and it's used as a roughing machining strategy. The concept behind it is defining an established or a constant engagement angle. Typically, it's a light radial engagement angle, and because of the light radial engagement angle, it reduces a lot of the tool load that you would experience and the tool forces that you would experience. And because of this, you can take a full depth of cut, a much larger depth of cut than your traditional milling techniques. And you can also really increase your feeds during this process. Because of these two advantages there, you'll get a reduced machining time, pretty drastic reduced machining time. We typically see a reduction of about 70% machining time reduction. And then it also minimizes your tool wear. Because of these two things here, you also have a reduced energy consumption. You're not running your machines as long per part, so you're not actually running your machine in total as long, so you have a reduced energy consumption. And these are highly intelligent cycles, so the cycle is constantly being optimized. And what I mean by this is with the traditional milling cycle, you typically have one feed rate output at the beginning and it runs that feed rate constantly. With profit milling, we're constantly adjusting the feed rate during the operation based on the engagement that the tool is in material. So it's a highly optimized and intelligent cycle, which is really nice. All right. So how does it work? It works by defining constant cutting conditions. So like I said, talking about a constant tool engagement angle, you're defining your radial engagement angle. And because you can define it as a lighter engagement angle, the radial cutter forces are not as high. So because of this, you can take full depth of cut and increase your feed rates. The chip load is a constant chip load. So when you're getting into corners and things like that, we're not actually getting fully engaged in corners where you would see high chip loads and high tool loads. It's a much reduced load on the tool when getting into corners. We reduce the feed as you're going into a corner, which is one of the advantages. We have optimized transition moves within the cycle. We have what are called micro lifts. So as it's doing its climb cutting, it's doing a radial move. Once it finishes that radial move, it does what's called a micro lift and goes back to the beginning. And it's actually a high feed move. It's not a rapid move, which is great because it's not the acceleration and deceleration forces on your machine are not really that great. They're not that high. So it's much easier on your machine and it results in much smoother transitions. And like I was talking about before, we have dynamic feed rate adjustments where it's constantly adjusting that feed rate during the cycle based on that engagement in material. So you're never really getting too heavily engaged in material. It's just a constant chip load that you're achieving there. So one of the concepts of it is chip thinning, and chip thinning is when the radial depth of cut is less than the radius of the milling cutter. And it's what you get is the thickness is less than the programmed feed per tooth, and this is what is known as chip thinning. Chip thinning is really what you're trying to achieve with this. With a shallower cut, in order to maintain the proper chip load, the cutter can be sped up using speed factors or feed rate multipliers. We can increase it typically by as much as 8 times your typical feed rate during these chip thinning milling processes. Chip thinning conditions also produce less heat during the cutting process due to the reduced radial engagement. And this is why you'll see a lot of times when you're running these types of cycles, you'll see those nice bluish and purple tinted chips. And that's because all of the heat is actually being expelled into the chip, not into the part and not into the tool itself, which is a great advantage. And what we can see here, and actually I'll go ahead and show you a video. So what we're going to see here is, oops, this is not the video that I wanted. Give me 1 second. This is one of the videos. This is a little preview of what profit milling looks like at the machine. All right. Okay, back to the presentation. So tool engagement angle. I've been talking a lot about tool engagement angle and radial engagement angle. And this is what I'm kind of explaining here. This is a visual of it. So right here, we can see what's a top-down view of the tool. And right here is our tool engagement angle. And this is what we're after. We're going to try to define a constant tool engagement angle. And we're going to typically define this as a lighter engagement angle. And it depends on your material type. I know with some steels, you typically define like a 25 to 35% engagement angle. And this is where you're really allowing your advantage of increasing the feed rate and the total depth of cut. Because we're defining a light tool engagement angle, you're reducing those forces on the tool itself. And on the left here, you can kind of see how we can come up with that tool engagement angle. It's using the width of the cut, also with the radius of the cutting tool are some of the inputs that go into that. Within ESPRIT, when you're defining these cycles in ESPRIT, there's actually a setting where you can just define that engagement angle. And it'll just do these calculations for you. It'll adjust the step over that you're using in the operation based off of your engagement angle, and that's all calculated in ESPRIT. Here's a visual on some of the forces that are typically experienced in these cutting cycles. So side cutter force and radial force is exhibited on each individual flute. And so for a 4-flute end mill, if the engagement is greater than 50%, 2 flutes will be engaged in the cut at all times. And this will actually produce multiple force vectors on the tool at different locations. And it changes the direction of the radial force exhibited on the tool during the cut. Increasing the radial depth of cut above 50% can change the direction of the radial force. And that can cause undesirable cutting conditions in the cycle. And this is just kind of what that diagram is illustrating here. And this is an example of the chip load. So chip load is used to determine the optimal feed per tooth for the cutting cycle. Recommended feed rates from cutting tool manufacturers are generally measured at 50% step over, where the chip is the thickness. During profit milling, we typically don't have a very high step over. Once you define your engagement angle, the step over is pretty low. And that again is what will reduce that tool load and reduce also the chip load as well. And there's a calculation there for how that chip load is calculated. Formula there for you. All right, I talked a little bit about micro lifts or back feeds. So what this is, like I said, it's a high feed move. And once our tool comes in and climb cuts and does that full radial movement, it does this little micro lift. The green here in this illustration is the actual cutting movement. And then the red line here is what that micro lift is. So it's just a slight lift up off of the part. So we're not dragging the tool along the part. And it's a high feed rate. And so in ESPRIT, you can see here, this would be a window right here that you would see. Whoops, let me go back. When you're defining the operation in ESPRIT, you can see up top, we can define the engagement angle. You just put the engagement angle you want to use. And then you can define the transition feed rate. And so right here, what they're saying is our transition feed rate when we're doing that micro lift is going to be 300% of the defined feed rate in the operation. And it is output as a high feed move. So it's much easier on the machine itself in terms of the acceleration forces and deceleration forces. All right. All right. I talked a little bit about dynamic feed rates. In the operation, a typical traditional milling operation, you'll have one defined feed rate, and that's what's used throughout the operation. However, when you start getting into corners and things, if we use that same feed rate throughout the corners, you'll typically get a lot of chirping and chatter. And one way to reduce that is to use a dynamic feed rate. And so right here on the right, you can kind of see what the G code would look like. We're constantly adapting and changing the feed rate, or changing it around so that when it's getting more engaged in material, it may reduce that feed rate, so we're not having too much, or we're not increasing that material engagement. In ESPRIT, you can define a max feed rate so that it'll never go above a certain feed rate. That way, it's just sort of like a safety move there. So you define a max feed rate, will never go above that actual feed rate. All right, so here's a conventional milling toolpath, and we'll take a look at some of the shortcomings that are caused from traditional milling toolpaths. So one thing I had mentioned is the high engagement angles, especially in corners. That's where you're going to get a lot of your chatter and chirping. The tool is getting really heavily engaged in those corners, and so what profit milling does is it kind of breaks up those corners and will just peck at the corner while reducing the feed rate. We eliminate a lot of these sharp corner movements here, which isn't ideal. You know, you're changing direction drastically on the machine, which isn't great for the machine. So a lot of that is removed with profit milling. The toolpath itself is just an offset of the actual profile, which can lead to some issues. Constant centerline feed rate, which isn't great. And then right here, full width slotting. We have options within the profit milling cycle to kind of deal with that full width slotting. So when that tool does get more heavily engaged, you're taking a more reduced feed rate, and also you can define an incremental depth for that. So here's a look at the actual profit milling toolpath, and we'll see a couple things here. First thing I'll start off is the corners here. You can see we're doing what's called corner picking, where it's not actually taking the full corner at once. We're controlling, like I said, that engagement angle, even in corners. We'll reduce the feed rate and just keep that radial engagement. So we're always taking a nice light radial engaged cut. We have smooth transitions. This is where it's going to use those micro lifts. So it does a full radius move there, does a micro lift back to the beginning, and does another full radius move. We're no longer having those sharp movements that we saw in the traditional toolpath. Trochoidal movement through these slots. So it'll still use your trochoidal strategy if it's able to through slots. If it's not able to do the trochoidal motion through a slot, we do have the option to switch to a more traditional toolpath, and you can define a lower feed rate when the tool is getting more heavily engaged or fully engaged in a slot. And you can also define an actual incremental depth for that. And here we just have the optimized feed rate, where it's constantly changing the feed rate based on that tool engagement. So the nice thing about ESPRIT is that our R&D department is in-house, and so we're constantly updating and improving our cycles, especially profit milling. And over the years, these are some of the improvements that we've seen within profit milling. And I'm going to talk about these a little bit more in depth, but we have large initial spiral, the bottom up strategy, which should always be used when using profit milling. That's where you really get your advantages from. You can define your max trochoidal width, which is just the width of your radial moves. You always kind of want to take the largest trochoidal width you can. And then now we have support for rotary milling cycles to use with profit milling. So here's the profit milling evolution. Here we have the large initial spiral. So what initially happens is the tool will do a helical move down to full depth of cut. You want to always try to get almost the entire flute length. And once it's down at that full depth of cut, what happens is it's going to start just doing large radial movements or spiral movements. And what this does is it allows for chip evacuation much better. It'll open up that initial pocket, and you get much better chip evacuation, and coolant can get into that pocket. Instead of just jumping right into the sort of small trochoidal movements, it'll do this large initial spiral. So profit milling is now supported on all of these cycles. So it was originally just 2.5 axis, 3 axis, and 5 axis, but we have introduced support for 4 axis cycles as well, so your rotary cycles. And in TNG, what's really nice is it's easy to set up here. Here, what we can see is a rotary cycle that, well, it should be doing that. It's a rotary cycle that uses profit milling, and previously it was a completely separate cycle. So if you use a ESPRIT 20X, it was rotary face pocketing or rotary face contouring. In TNG, we don't have two different cycles. It's just an option within your pocketing or contouring cycles. So if you want to use the rotary axis and keep the tool on Y center line, all you have to do is just hit yes to the rotary option within the operation. All right, so bottom up Z-level roughing. This is where we always recommend using a bottom up strategy. So a traditional milling strategy would be what's called top down. That's not ideal because you're only using a portion of the end mill, the bottom portion of the end mill. Where the advantages come with profit milling is going to a full depth of cut, taking out as much material as you possibly can with that full depth of cut using that full flute length. And then we work up by a defined incremental depth. That's where your advantage comes from with the ESPRIT. We don't recommend doing a traditional top-down milling. It's always bottom-up roughing is much better. And I'll go ahead and show you a video on that. At incremental depth and working its way from bottom to top. This is the concept of bottom-up roughing. And I'm just going to show another video real quickly. Oops, not this one here. This is the rotary. So here what we see is the rotary cycle using profit milling. What we are seeing here is the tool is actually on Y center line. We're not actually using the Y axis at all. So if your machine is lacking a Y axis, you can still use profit milling with this for a rotary cycle. And again, this is easy to define in TNG. It's just a switch on whether you want to use the rotary axis or not. Okay, bottom up roughing, again, it's just an option within the cycle itself. And here's just kind of an illustration on what's happening. So it comes down full depth, takes as much material as it can, and then steps its way up based on a defined incremental depth, which would be here. And then it would go down again to a full depth of cut, mill out as much as it can, and then work its way up. This is one of the improvements, as well as controlling the max trochoidal width. So here you can see we have the option to control that, to control the trochoidal width. And here you can see the difference between a 200% trochoidal width and a 400. The radial moves are much larger width than the 200. We always recommend using as large of a radial width as you can, or a trochoidal width as you can. All right, so I've been talking about increased feed rates. One of the ways you come about these increased feed rates is by creating what's called the compensation factor. This is the formula for the compensation factor. And this will give you how many times you can, once you run through this compensation factor, you can multiply the feed rate by the compensation factor. Obviously, this is a lot of math to do here. John Pusatera, who's coming up next, is going to talk about a calculator, an app that Sandvik has that actually will do these calculations for you. You just need a couple inputs. Once you put the inputs in, it'll actually do this calculation for you, which is really nice. So for profit milling, there are some considerations that you need to know. So you need to know the machine limits. The nature of the cycle itself, it's going to be, because of our high feed rates, it's going to be also high RPM for the machine. So you need to make sure that the machine is capable of reaching those RPMs needed for the optimized cycle. You also need to have proper tool and work holding. We typically recommend shrink fit or hydraulic holders for this. You know, you get with these high RPMs and high feed moves, you really want to have some proper tool holding there. You need to decide whether speed or power cutting is what you're trying to get here, what your goal is, and just make sure you get properly trained on profit milling. Make sure that you understand what the inputs are and what settings are going to optimize your operation for exactly what you're trying to do. There are some machine tool control settings. So each machine is going to typically have settings for high-speed machining, and I'm just going to go over a few of those quickly. So on Mazak, you have your geometry compensation, which is G61.1 and G64. I mean, you just want to make sure that those inputs at the control are put in properly for your high-speed machining. For Akuma, you have high cut mode, G131 and G130. And again, you would want to make sure that like your J parameter is set to high speed for this. DMG MORI, you have G332, which is your cutting mode. Again, these are just some parameters that you would need to make sure are set properly at the control. And if you have a Heidenhain control or Siemens control, you have cycle 32 or cycle 832, which is your high-speed machining cycles. You're going to make sure that you want to use those. And just some customer feedback. So this is kind of just some of the returns that customers have seen using profit milling. So you can see tooling cost was drastically reduced. You know, tooling cost for a slot was $700 per part for the inserts. And now using the new method, it dropped that cost to $175 per tool, and the tool life will now achieve 10 parts. And also the reduced cycle time, they reduced 10 hours per part, 100 hours saved on 10 parts. So you really start to see a return on investment when using profit milling. These are just kind of some statistics that you can see here on where that return on investment is coming from. Lastly, I'm just going to talk quickly about high feed mills. In ESPRIT, we have the ability to define a high feed mill, and the big thing here is going to be defining this orientation angle. You're going to want to make sure that this orientation angle matches the insert orientation angle on the high feed mill. And then Brent was talking about doing some rolling in moves. This is a visual of that. I can actually, we'll see this later, but the roll-in move is a default option within TNG. So if you have to use the mold Z-level roughing, but in the links, the entry move is called radius and lateral plane. And just the default settings for that operation, it'll achieve that roll-in move that Brent was talking about. What you may just want to control is actually the size of the roll-in move, which is easy to control within TNG. It's just changing one parameter. Yeah, and that's my presentation. So I am going to jump over to John.
Good morning. Well, good morning, everyone. This is John Pusatera. I'm a senior training specialist at Sandvik Coromant. And what the guys asked me to do today was talk about how we can help you compensate for chip thinning using a calculator. So before I do that, though, what I want to do is I want to go back up here and show you what a hydraulic holder looks like in action. So when you look at a hydraulic holder, we're using this one with high feed side milling exactly right. So we're using, and you can see it down here, we're using a very large axial depth of cut and a very small radial depth of cut. We would say to our customers that we don't want the radial depth of cut with high feed side milling to exceed 20%. But we actually find that there's more of a sweet spot in that 8 to 12% area. So you'll have to do your own experimenting based on what you're cutting and how you're doing that to get the best cubic inches of metal removed in a minute. But before I show you how to compensate, I just want to show you why we want to use a hydraulic chuck or shrink fit. And I'm going to go to that slide here, which you already saw. But you can see the hydraulic holder on the left here, and then you can also see shrink fit next to it. And what makes these so valuable in this type of work is these top two categories. So you're seeing pull-out security. So the ability of the holder to have tremendous clamping forces on the tool. And both of these products do exactly that, tremendous clamping forces. So you don't have the tool likely to be pulled out of the collet. So that's important. And that also, the reason that's important, it allows you to use higher helix angles when you need that, because higher helix angles are going to want to pull those end mills right out of the chuck. So those do a good job there. The other thing that they do so well is they have minimal run out. So what is minimal run out? We're talking about at 3 times the tool diameter. So let's say we have a 1/2 inch tool sticking out 1.5 inches. We have about 1.5 tenths of run out there. As opposed to other products, let's just go to the Weldon chuck as an example. It has about 2 thousandths of run out. So 2 thousandths here, these two have about 1.5 tenths. What makes that so important is for every 4 tenths of run out, you lose up to half of your tool life on your perishable tool. Now that's going to be even more exaggerated when you have really small tools. So let's say 1/8 inch and under, or 3 millimeters and under. So keep that in mind. While a Weldon chuck or an end mill holder, very inexpensive, and a hydraulic holder or a shrink fit system, expensive, but these are one-time purchases where you're going to be buying the perishable item over and over. So with that, I wish to go back to the app. So I have my Sandvik Coromant apps here, and these apps are all free. So you're welcome to download them. I'm going to focus just on this app today in the few short minutes that we have left. But this is going to allow you to do what Kevin just talked about, and that's to compensate for your low engagement, your low radial engagement, your side milling. So let's go in there. So I'm just going to go in there. By the way, I'm utilizing an app called Smart Mirror that allows me to put my phone onto my laptop here. And when I open up my milling calculator, what I want to do first and show you first is I want to go down here to more. And I'm going to go in there, and then I'm going to go up here to units of measure. When you download this free app and you're in the United States, I'm coming to you from Chicago area today, it's going to download in automatic. Okay, and then it's going to say, well, John, you're in the Chicago suburbs, you want to be an inch, but it's going to automatically do that. Well, maybe I don't, and maybe you don't. So you have to set that if you choose. If you work in metric a lot, well, just set it in metric. If you do both like I do, I just like to set it for what I need. So you make the call there. The other thing I want to point out, I'm going to go back here, is lead angle or entering angle. Entering angle is showing you how that works. These are both giving you the same information. It just depends on how you're talking. Typically, everybody, when it comes to milling, uses entering angle. So I'm going to stick with that. So you can see it's a 10-degree entering angle in this example that we're showing you here. So I'm just going to leave that for you there. And then I'm going to go back to my calculator. And the calculator is simple. All we're basically doing here is we're just filling out a form. How easy could it be? So if we just take up a fictitious example, and I'm going to stick with Kevin's theme of the high feed side milling. So I'm going to take a 1/2 inch diameter cutter here. And then here, when it comes to cutting speed, I can either enter surface footage or I could enter RPM. I can do this either way. I'm going to go ahead and enter surface footage. But once I do that, oops. Once I do that, it's going to calculate the RPM for me. So no big deal. I mean, you could do it either way. I could clear that. And I could put in the 6,000 RPM here and do the same thing. So it just depends on where you are. You're sitting at your desk and you see the surface footage recommendation. You're standing by the machine and you see the RPM. It's your choice. You do as you wish there. Now I'm going to stick with also what I just said about when we use proper tool holding, and that really is hydraulic or shrink fit, we can get away with large axial depth of cut. So I'm going to stick with that 3 times that I talked about, or the maximum flute length if we can. And I'm also going to stick with our theme of small radial engagement. So I'm going to choose 50 thousandths, which is going to give me 10% engagement here. And the reason I'm doing this is anytime you have less than half of your cutter engaged in the workpiece, and that's what the picture is trying to show you here. If we were right down the center of this tool, which would be somewhere right about here, the chip would be at its thickest moment. You could see at some point, the chip is going to reduce to nothing. This is known as chip thinning. So we have some chip thinning shown here. Well, certainly my example of a 1/2 inch tool only utilizing 50 thousandths has chip thinning. So how do we calculate that? Well, we don't have to do anything really other than give the calculator the proper information. So the next decision we make is we are side milling. We do have an entering angle of 90 degrees, but I want to show you something here. You can go in here and choose other entering angles. Your choice. I'm going to stick with 90. I saw Kevin use the 90-degree end mill on his presentation, so I'm going to stick with that. And we have 10% engagement, so we know there's chip thinning taking place. How much chip thinning? What's the multiplier? Well, we don't know that. We could calculate that using the formula that Kevin showed, but I'm just going to put the data into the app here. So as a cutting tool person myself, I work in chip thickness because I'm always around cutting tools like you see here. I'm always working with cutting tools. So I always want to control the chip thickness because when we have too thin a chip, when you're machining angel hair on your vise, that's like a sliver, that's too thin. So we don't want that. We want to make sure there's thickness there. So your 1/2 inch end mill might say, you should have a chip thickness of 1/1000 And now you can see when I put in the 1/1000 it has compensated for our application here. So we have a 10% engagement, our 1/2 inch tool, 50 thousandths engaged. And so when we want a 1/1000 chip thickness, it's going to tell us to feed that at 2 thousandths. So compensation is basically complete there. Just real brief, I just have a minute or two left here. What I want to just show you is I want to populate the information up here just so you can see how this works, and then I'll stop. So I have to put in number of teeth, and I'm going to say we have 4 teeth. And I'm going to say the length of cut is 14 inches. And we're taking we'll say 3 passes. And then this last piece of information that I'm going to enter for you is just trying to get the horsepower correct. So we're trying to narrow down your specific cutting force. So an example is if you were using steel as your baseline, Inconel would be more specific cutting force. And steel versus aluminum will be less cutting force. That's what we're trying to do here. So when I enter this memo pad here, I'm going to choose what we demonstrate in our application areas all the time. And so I'm going to do that. I was just demonstrating this a few minutes ago. So I'm going to go in here to the material groups. I chose steel. I'm going to choose number 2. I'm going to go back to number 1. And this is basically a 4140, which we do a lot in our training facilities around the world. So now what that's done for us is it's populated all the data up here. So let me just show you what that is. And I'm going to go backwards here since I'm already here at torque. So I'm just going to swipe from left to right now because I'm at the end. So we have the torque value. We have the horsepower. How much horsepower do we need for this cut? And then how long does it take for the whole cycle? That was all of our passes. And then how much per pass? And then how many cubes of metal are we removing? And then what's our inches per minute? So that's as simple as it is. It's just a simple calculator. And I would recommend that you grab them and utilize them and take advantage of the simple free tool. And with that, Kevin, I'm going to turn it back over to you.
All right, let's
share with you. I'm going to share with you now.
Okay, perfect. I can take the screen. All right, so that kind of wraps up the presentation. I think we'll move into the Q&A session. We've been going through and answering your questions that you've been typing up and sending in to us. I think, Dan, did you want to take a look at some of those or go over some of those questions?
Yeah, so I can just go down the list here. There are a few. There were a couple questions asked about prime turning, which is a cycle that Sandvik supports. And we do have the ability to program that type of cycle, although we don't have a dedicated cycle. And we'll be going through some of those techniques along with our profit milling cycle in the third session of this webinar series, which is going to be dedicated to modern machining methods for turning. So hopefully it answers that question. There was another question, possibly for Brent or John. They were asking about how many flutes do you guys recommend for the type of profit or for profit milling? How many flutes on an end mill do you typically recommend?
What we would say, and I'll let Brent answer as well, but what we would say is when you're doing side milling, like the example I just gave you, if you have a 1/2-inch tool with only 50,000 depth of cut, you don't need deep gullets when you're using these tools correctly. So I would say more teeth in that example. So anytime you're using these modern techniques, we're looking for more teeth.
Yeah, I would agree with that, John. I really have nothing more to add. You don't need the deep gullet. You're right.
Okay, let's see. So somebody else was asking whether or not the microlift can be disabled, and there's not an option to do that. And the reason is because the microlift is how we achieve such good tool wear with the cycle. So our tool life is drastically increased by a variety of factors, and the microlift is one. So the microlift basically lifts the tool up as it transitions into the next cut. So even though the material on the floor has already been cut, if you were to take a section view of it and look at it closely, you would see that it's not a perfectly flat surface. So if we were to drag the tool across that surface, especially at a high rate of feed, typically you're going to be running anywhere from 200 to 500% of your original program feed rate during those back feeds. If you were to drag the tool across the surface at that high feed rate, you would inevitably wear the tool out much faster. So there's not a way to disable it, and the reason is because it's one of the ways that we're able to gain such drastic tool life increase. So there was another question. It looks like I think maybe Brent answered about whether or not the tools that you were talking about are going to be off the shelf.
Yeah, right. I've been in meetings about that for the past few weeks. We're trying to decide what assortment, Yes, the answer is yes, but there'll be metric sizes to begin with. So instead of a 4-inch cutter, it'll be 100 millimeters. And instead of 5-inch, it'll be 125, to begin with anyway. So, but that's in the works.
Okay. So somebody else was asking, are the cycle times typically shorter using profit mill versus conventional milling? And the answer was yes. Typically, we see at least a 70% cycle time reduction using this profit milling cycle in comparison to conventional cycles. And let's see.
Dan, I would say in addition to that, you're going to have a lot better tool life too, because of the proper utilization of the tool.
Yeah, that's true. I mean, we generally see, anywhere from 5 to 10 times the tool life that you would see in a conventional cycle. And part of that is due to the microlift. Also the fact that, the light radial engagement reduces loads. So let's see, Kevin, did you talk about the roll-in technique?
Yeah, so within the Z-level roughing operation, you will have the
Yeah,
ability to
somebody was
find an
asking
entry.
about that. If you could maybe elaborate on that a little bit.
Yeah, in order to achieve that, you do have, so I think the question was whether that was available in just the traditional facing operation. You do have to use the mold Z-level roughing cycle to achieve that. It's really easy to do once you get that set up. It's just the default option will use that roll-in, and then you can just control the size of the roll-in. It's just you can control the radius size of that roll-in move on the links page for the entry move.
Okay, somebody else was asking about any tips for getting the chips out of a deep pocket when you're using the bottom up strategy. And there's a few things that help with that. You know, one is the fact that larger initial spiral that is produced by the cycle should create a large enough area for you to be able to direct air into the cavity and keep the chips blown out so that you're not recutting them. And as Kevin was talking about, that's also where your tool life comes into play, because the heat that is in the chip is evacuated out of the cavity. So it's not breaking down your tool. You don't have the heat in the part and in the tool, which is just going to you know, kill your tool life even faster. So yeah, we generally recommend air blow, and that large initial spiral should allow you to direct the air blow down into the cavity and blow the chips out. Actually, you can see it pretty clearly in that first video that Kevin showed. So I think we pretty much have most of the questions.
Hey, Dan, it's Brent again. And what you just talked about, the air blast and getting rid of chips and such, it reminded me of something I think I forgot to mention when I was presenting the M5 series of cutters. They're designed for through coolant or through the tool MQL, which is, you know, MQL is like an air blast with a mist mixed in with it. And yeah, they'll work either way, or they'll work with traditional flood coolant. So anyway, I just thought I better add that. Thank you.
Yeah, appreciate that.
Okay.
So I don't see any new questions. Probably the last one, which isn't answered yet because I didn't understand it completely, but one of the attendees was asking, does profit milling consider any thermal load on the tool when determining its path? And to me, that would mean areas of high engagement. So the corners, anywhere that you have full width slotting, where you have material on both sides of the tools, both of those areas are addressed. As Kevin was talking about earlier, you have the corner picking in the corners to, you know, remove small bites of the material in those areas of high engagement. And then also for the slotting, you're either going to get the tricordial motion, or you can revert back to a conventional slotting cycle where you can slow the feed rate down and take a smaller incremental depth.
And another thing in that regard too, that John mentioned how important chip thickness is, and and how you don't want those little razor thin chips. That will cause the tool to overheat, which of course can go into the holder and into the spindle and cause all kinds of other issues. So yeah, you want to maintain enough feed rate and use that calculator that John showed so you can get enough chip thickness to get the heat into the chip, not into the tool.
Exactly. So yeah, I think that's pretty much it. I don't see any new questions popping up here, so I guess we'll go ahead and end this session. But before we do, I just want to remind you that 2 weeks from today, we're going to be doing our second session, which is going to be on hole making. And there are a lot of advancements in ESPRIT and ESPRIT's hole recognition abilities. And then within the drilling cycle, there's a lot of new options. And we really want to show you guys that stuff. So that'll be the next session, which is May 14th at 11 a.m. Eastern Standard Time. So I appreciate everybody attending today, and thank you to the presenters. And we will see you in the next session.
Thanks everybody.
Thanks everyone.
Thanks, everyone.